You know that battery in your phone, or the one in your car key, or your remote? It feels so ordinary. But its origin story is absolutely wild. It's a story packed with twitching frog legs, intense scientific rivalries, and an invention that literally built the world we live in today. So let's get into how it all started. And look, that is zero exaggeration. We're not just talking about powering a few gadgets here and there. The invention of the battery laid the actual foundation for our entire electrified world. It was a complete shift in how humanity relates to energy. You have to remember, before the battery, electricity was just chaos. Think about it, lightning, or maybe the quick, violent zap from a Leyden jar. It was more of a fun parlor trick than a useful tool. The battery changed the whole game. It's what tamed the electron, turning it from this wild, unpredictable flash into a steady, controllable river of current that we could finally put to work. So how did we do it? How did we tame that wild electron? Well, the story is pretty incredible, and it doesn't start where you'd think, like in a physics lab with wires and magnets. Nope. It starts with a really bizarre debate, all about a dissected frog's leg. This was the central question, the big debate. So you've got this Italian physician, Luigi Galvani, and he notices that a dead frog's legs twitch when he touches them with two different kinds of metal. He was absolutely convinced he'd discovered animal electricity, some kind of vital life force that came from the tissue itself. But another scientist, a physicist named Alessandro Volta, he wasn't buying it. And here's where they really disagreed. Galvani thought the frog's leg was the generator, the thing creating the electricity. But Volta, he argued that the frog's leg was just a very sensitive detector. He was sure the real source of the electricity was the contact between those two different metals, especially in a moist environment. And this little disagreement kicked off one of the most productive rivalries in the history of science. So Volta, to prove his point, decided he had to take biology completely out of the equation. He set out to build a device made of nothing but metal and liquid. And in the process, he kind of accidentally invented the first true battery and, changed the course of history forever. So in 1800, Volta shows off his creation, the voltaic pile. And it's so simple, you could almost build it yourself. You just take a zinc disc, then a piece of cloth or cardboard soaked in salt water, then a copper disc, and then you just repeat the stack. That's it. This incredibly simple design was about to do something no device in history had ever done before. And boom, it produced the world's first steady, continuous flow of electric current. I mean, within weeks of Volta's announcement, scientists everywhere were using it to do incredible new things, like splitting water into hydrogen and oxygen. This wasn't just a cool new gadget, it gave birth to an entire field of science, electrochemistry. But for all its genius, the voltaic pile had a fatal flaw. It worked, and it worked wonderfully. For a few minutes, and then the power would just nosedive. This was the very first major bottleneck in energy storage, a problem that honestly still echoes in our own search for better batteries today. The problem was a chemical one, a phenomenon that engineers would wrestle with for decades. It was called polarization. And really, it just meant the battery was choking on its own exhaust. Okay, so here's what was actually going on. As the battery was doing its thing, the chemical reaction was creating these tiny little bubbles of hydrogen gas, and they were sticking to the surface of the copper plates. Now, that might sound like a small detail, but this gradual buildup of gas turned out to be a complete showstopper. See, these bubbles basically formed an insulating blanket over the metal, physically stopping the liquid electrolyte from making contact. This not only blocked the reaction, but it also created a reverse electrical force that was actively fighting against the current. The result? The voltage would just plummet after only a few minutes of use. And as if that wasn't bad enough, the physical design was, well, it was a mess. It was a vertical stack, so the weight of the metal discs would literally squeeze the salt water out of the cloth separators. This led to leaks, short circuits. It was just a wet, unstable device that didn't last very long. So the path forward was pretty clear, right? If the battery was ever going to be a truly useful tool, somebody had to solve two big problems: its messy, unstable design and its fatal chemical flaw. The mechanical fix actually came pretty fast, just 2 years later. A guy named William Cruikshank had this simple but brilliant idea. Instead of stacking the plates vertically, he just laid them horizontally inside a sealed wooden box. creating these little troughs for the acid. This immediately solved the leaking problem and even let him use bigger plates. It was really the first battery designed for mass production. But that chemical problem, polarization, that was the big one. And the real game changer wouldn't show up until 1836 with an invention from a British chemist named John Frederick Daniel. And his solution was just beautiful. The Daniel cell was incredibly elegant. It used two different chemical solutions, or electrolytes, and it separated them with a porous clay pot. Now this pot was the key. It let ions pass through to complete the circuit, but it kept the two main liquids from mixing. This clever two-liquid system totally changed the chemistry of the reaction. Instead of creating those pesky hydrogen bubbles, it deposited solid copper onto the electrode. Problem solved. And I mean, the difference this made was just night and day. Look at the voltage stability. Where the voltaic pile would die off in minutes, the Daniel cell provided a constant, reliable voltage for hours on end. This one innovation transformed the battery from a short-lived scientific toy into a dependable industrial tool. Now, it still had its own flaws. It was fragile, you couldn't really move it around, but for the very first time, reliable, long-term power was finally a reality. So you've just invented the world's first source of reliable, steady power. What do you do with it? Well, you build a communications revolution. You build what we'd now call the Victorian Internet. The Daniel cell consistently produced a steady, predictable 1.1 volts. That number might not sound like much, but it was everything. For decades, this consistent voltage became the gold standard, the benchmark that powered the modern world's very first great electrical network. And this is exactly why people call it the technological bedrock of the Victorian Internet. We're talking about the electric telegraph. Before the Daniel cell, sending Morse code over long distances was a nightmare. The power from a voltaic pile was so unstable that the signal would fade and distort, becoming totally useless. The Daniel cell's steady, unwavering current was the key that finally unlocked reliable, continent-spanning communication. So its legacy? Oh, it's huge. This reliable power source is what allowed the telegraph to weave this incredible web of wires across continents. This network coordinated train schedules, preventing collisions. It transmitted news in minutes instead of weeks. It let governments manage globe-spanning empires in near real time. This was the moment the battery went from a lab experiment to a genuine engine of global change. Welcome to The Explainer. We're going to talk about something you probably never think about, at least not until your car won't start, the humble car battery. But what if I told you that its story involves broken bones and an incredible ironic twist that shaped the entire modern world? So yeah, a broken jaw and a car battery. How on earth could those two things possibly be connected? It sounds totally bizarre, I know, but the answer uncovers this amazing story of invention, tragedy, and an irony that put the gasoline engine on the road to complete dominance. All right, to really get the car battery, our story has to start way back in the mid-1800s, a time when all batteries had one giant, really frustrating problem. See, back then, the world only had what were called primary cells. Just think of these as single-use devices. Once the chemical reaction was done, they were basically garbage. You either had to toss them or go through this incredibly expensive and inefficient process to rebuild them. And honestly, this analogy just says it all. Can you imagine having to rebuild your entire engine after every single tank of gas? That's how wasteful and impractical this whole system was. The world was desperate for a breakthrough. And that breakthrough finally arrived in 1859, thanks to a French physicist who invented the world's first practical rechargeable battery, what we now call a secondary cell. His name was Gaston Planté, and his design was just chemically brilliant. It was based on two super simple materials, lead and sulfuric acid, and a chemical reaction that, and this is the crucial part, could be run in reverse. That meant the battery could be recharged over and over again. He made this thing he called a jelly roll by spiraling two long lead sheets together with some rubber in between. When he ran a current through it, it stored energy. When he discharged it, it released that energy. But unlike every battery that came before, you could then just recharge it. It was a complete revolution in a jar. But there was a catch, and oh man, it was a huge one. To get a single battery ready for use, it had to be formed, which meant charging it and discharging it over and over again for months. This made them unbelievably expensive to produce, so they were stuck in really niche uses, like lighting for train cars. So, let's fast forward to 1881. It's going to take another inventor to finally crack this manufacturing nightmare and unlock the battery's real potential. An engineer named Camille Faure came up with this absolutely brilliant workaround. Instead of waiting months for the active material to form, he just created a paste of lead oxides and literally pressed it onto a lead grid. This one simple change was a total game changer, slashing production time from months down to just a few hours. And the impact was immediate and massive. Suddenly, you could mass produce these batteries. Power plants could build giant walls of them to store surplus electricity, creating the first truly stable power grids that could deliver energy whenever you needed it. But the battery's most profound and totally unexpected impact wasn't on the grid at all. It was on the road, where it would solve a really dangerous and sometimes fatal problem with the first cars. So, early gasoline cars had to be started with this enormous hand crank. The driver had to physically turn the entire engine over. If that engine fired at just the wrong moment, something called kickback would send the crank handle flying backwards with enough force to cause just horrific injuries. We're talking broken arms, skulls, it was no joke. And then in 1910, that danger became a real tragedy. A man named Byron Carter stopped to help a stranded driver. While he was cranking the engine, it kicked back and shattered his jaw. He actually died later from the complications. Now, the tragic twist here, Carter was a close friend of Henry Leland, the head of Cadillac, who was so completely devastated he vowed to get rid of the hand crank forever. So here's the crucial point. Getting rid of the crank meant you needed an electric motor powerful enough to turn the engine, and that motor needed a powerful, portable energy source that could deliver a massive burst of electricity on demand. An inventor named Charles Kettering designed the electric starter motor, but it had this incredible power requirement. To turn a cold, heavy engine, it needed a huge surge of current, hundreds of amps, all at once. That was way more than any typical battery at the time could handle. The solution lay in a specific property of the lead-acid battery, its incredibly low internal resistance. Okay, think of it this way. Resistance is like a narrow pipe. It chokes the flow of energy. But the lead-acid design was like a massive fire hose. It had almost no opposition to the flow of current, which meant it could unleash a colossal amount of energy in an instant. And this is what made all the difference. That low resistance allowed the battery to dump that enormous surge of power almost instantly, turning the engine over with ease. Literally, overnight, the gasoline car went from this dangerous, brutish machine that you had to be strong to start to something anyone could operate with just the push of a button. And this is where we get to the central, absolutely mind-blowing irony of the whole story. The battery, this amazing electrical device, ended up being used to solve the single biggest problem with the gasoline car. It made them so safe and easy to use that the early electric cars, which used the same heavy batteries but had terrible range, just couldn't compete anymore. So, instead of kicking off an electric age, the battery accidentally guaranteed a century of gasoline dominance. It became just a helper, right? A little sidekick for starting the engine and running the lights in a system that it could have and maybe even should have replaced entirely. And it would stay that way for nearly 100 years. Have you ever really looked at one of these? A simple AA battery. It's everywhere, in our TV remotes, our kids' toys, pretty much everything. It's one of the most common objects on the planet. But believe it or not, it has this wild story behind it. A story of genius innovation, of bitter corporate feuds, and even warring bunnies. All right, let's get into it. I know, it sounds like the setup to a really weird joke, right? But these three things are all pieces of the same puzzle. They're connected by a single, game-changing invention that totally reshaped our world. So stick with me because we're going to connect all these dots and uncover the hidden history of the little battery that runs our lives. Okay, so our story really kicks off with the simple problem, portability. Back in the 19th century, the big issue with batteries wasn't just power. It was that they were, wet. They were filled with sloshing, corrosive liquids. You definitely couldn't just pop one in your pocket. So the race was on to invent a dry cell, a power source that wouldn't leak all over the place. So how did we get there? Well, it all starts back in 1866 with Georges Lake-Lachant. He patented the ancestor to our modern disposable battery, but it was still a wet cell. The real breakthrough, the game changer, came 20 years later when Carl Gassner figured out how to turn that liquid electrolyte into a paste. Boom, the first dry cell was born. And what do you do with a new portable power source? Of course. Just over a decade later, in 1898, they used it to create the very first flashlight, giving people a safe, portable light they could take anywhere. Now, this zinc-carbon dry cell was a massive success. I mean, it became the standard for the next 60 years. But it had a huge, leaky problem. As our gadgets got more advanced and more power-hungry, we're talking motorized toys and radios now, the flaws in this old tech became really, really obvious. And you can see the fundamental issue right here. The old battery was fine for things that just needed a quick jolt of power, like a doorbell. But for anything that needed a steady stream of energy, like a toy car or a radio, it would die out super fast. And the worst part? The battery's own zinc casing would literally eat itself away and leak corrosive acid, often destroying the very device it was supposed to be powering. Ouch! So by the 1950s, people were just fed up, and so was a Canadian chemical engineer named Louis Urey. He was working for Eveready in Ohio, and his bosses gave him a simple task: just make our old batteries last a little bit longer. But Urey, he didn't want to just tweak it. He wanted to completely reinvent it from the ground up. Urey's approach was to change literally everything about the battery's chemistry. First, the anode. He swapped out the solid zinc can for powdered zinc, which created a much faster chemical reaction. Then he used a better material for the cathode. But the single most important change, the absolute masterstroke, was the electrolyte. He switched the whole thing from being acidic to being alkaline. Now, what does that mean? Well, he used a substance called potassium hydroxide, and this one change was the key to everything. The alkaline chemistry didn't just provide way more power density, it also stopped the nasty chemical reaction that made the old batteries corrode and leak. The biggest problem was finally solved. So you've just created what you think is the future of portable power. How do you convince your bosses? Well, Urey knew he needed something dramatic, so he staged a simple race in the company cafeteria. 2 identical toy cars. One had the best zinc-carbon battery they made, the other had his new secret alkaline prototype. And the result? It wasn't even a contest. The car with Urey's battery just kept going and going and going. It ran laps around the cafeteria long after the other car had sputtered to a halt. Can you imagine seeing that? It was undeniable proof that he had created something vastly superior. So Eveready introduced the world's first alkaline battery in 1959. And you think, great, end of story, right? Nope. Inventing a revolutionary product is one thing. Selling it is a completely different ballgame. And the company suddenly faced a very strange new problem: their own success. You have to understand, Eveready was the king of the cheap battery market. They were worried that if they pushed this new, more expensive but much longer-lasting battery too hard, it would kill their cash cow. People would just buy fewer batteries overall. And this hesitation, this fear, created a huge opening for a rival company called PR Mallory, who would soon rebrand their battery division into a name you definitely know: Duracell. And this, my friends, is where a corporate rivalry explodes into one of the most famous marketing showdowns in history. I'm talking about the Great Bunny War. Duracell saw the opening Eveready left them, and they charged right through it, sparking an advertising battle that gave us 2 of the most recognizable mascots of all time. So let's meet our 2 contenders. In one corner, you've got Duracell going all in on marketing the long life of its copper top battery. And in the other corner, you have Eveready, which later becomes Energizer, playing catch up and deciding that the best way to fight back was to make fun of their competitor. So in 1973, Duracell launches this ad with a cute pink bunny drumming away, showing how it outlasts all the other toys. And it was a huge hit. It was so effective that 16 years later, in 1989, Energizer decided to launch their own bunny. This one had sunglasses, a cool attitude, and his whole purpose was to be a direct parody that would literally crash through the Duracell-style commercials. And here is where the story takes an absolutely bizarre twist. In a massive oversight, Duracell had actually let its trademark on the bunny character lapse in the United States. Energizer's lawyers spotted it, pounced on the opportunity, and legally snagged the rights to the bunny mascot, but only in North America. This blunder created the weird global divide that we still have today. If you're in the US or Canada, you know the cool Energizer bunny that just keeps going and going. But pretty much everywhere else in the world, the original cute pink Duracell bunny is still the face of long-lasting batteries. Two different bunnies for two competing brands, literally split by geography.
But here's the most important takeaway from all this. Beyond the funny commercials and the legal battles, this intense rivalry was fantastic for us, the consumers. The constant pressure to be better than the other guy forced both companies to pour a ton of money into research and development. This led to huge improvements in how batteries were made, how long they lasted on the shelf, and most importantly, how well they were sealed to prevent leaks.
Have you ever stopped to think about the battery in, say, an old power drill? Probably not, right? Well, it turns out it's part of this incredible story about a technology that completely reshaped our world. And not just once, but twice. We're about to dive into the story of the battery that kicked off our first cordless revolution and then, somehow, found itself right at the heart of the electric car's controversial first chapter.
So what's the connection? What possibly links an old Black & Decker, the very first Toyota Prius, and what some people call a lost decade for EVs? Well, the answer is a single, often overlooked battery technology. And let me tell you, it is a wild story of amazing innovation, really frustrating limitations, and a corporate saga that, some argue, basically slammed the brakes on an all-electric future. It all kicks off with our simple need for power you could carry around in your hand.
Okay, so picture this. It's the middle of the 20th century. We are inventing all these awesome new gadgets, right? But they're all stuck on a leash, tethered to the wall socket. The world was desperate for a reliable, rechargeable battery that wasn't, a massive lead-acid brick like the one in your car. And the solution? It came from a chemistry built around nickel. And just like that, the cord was cut. All of a sudden, we had this newfound freedom. The very first generation of these devices, the cordless shavers, the power tools, those handheld vacuums, the camcorders, they were all powered by one specific invention, the nickel-cadmium battery. You probably know it as NiCad. This thing was the workhorse that made portability a reality for millions. But what's really wild is the huge gap between when this thing was invented and when you could actually buy one. The NiCad battery was invented way back in 1899. But for decades, it was just too expensive and too tricky to produce. It wasn't until a manufacturing breakthrough in the 1950s, this process called sintered plate construction, that they finally became cheap and safe enough for us to get our hands on them. For all its game-changing power, though, the nickel battery had some serious skeletons in its closet. Two massive problems that would eventually seal its fate and really create the urgent need for its replacement. The first problem was something that frustrated pretty much anyone who ever used one. It was this bizarre, almost spooky phenomenon that made it feel like your own battery was fighting against you. People started calling it a technical poltergeist, which became known as the memory effect. Okay, so here's how it felt. Let's say you only used, 20% of your power tool's battery before you put it back on the charger. And you did that again and again. Well, the battery would start to remember that 20% mark. The next time you needed the full charge, your tool would just die right at that point, acting like it was empty, even when it had 80% of its juice left. It was maddening. Now, of course, it wasn't a real memory. What was actually happening was a physical change deep inside the battery. All those partial charges caused the tiny little cadmium crystals on the anode to grow and clump together into big, stable ones. And those big, chunky crystals, they had way less surface area, which meant the battery just couldn't push out its power at a high enough voltage. That's what caused that sudden voltage drop that made your device shut down. But the second problem, well, this one was way more serious. Cadmium is just an environmental nightmare. It's a highly toxic heavy metal, incredibly dangerous to our soil, our water, and to our health. And as millions, then billions of these batteries were being thrown out, regulators started to crack down, and the entire industry found itself in a real crisis. So, the industry needed a hero. They needed a new battery that worked just as well as the NiCad, but without that frustrating memory effect and, without the poison. The solution came from a class of materials that could do something absolutely remarkable with hydrogen. This was the dawn of the nickel metal hydride battery, or NiMH. The secret sauce here was the discovery of special metal alloys that could literally soak up hydrogen atoms and hold on to them. The best way to think about it is like a metal sponge for hydrogen. A pretty amazing concept, right? And that idea would become the foundation for a brand new, non-toxic battery anode. So here's the brilliant swap they made. They kept the reliable nickel part of the battery, the cathode, but they ripped out that toxic, memory-prone cadmium anode and replaced it with this new hydrogen sponge. And the result? A battery with no toxic heavy metals, way less memory effect, and, as a huge bonus, it could store a lot more energy. A key player here was an inventor named Stanford Ovshinsky, whose work on disordered alloys really made these batteries tough enough for commercial use. Now, while NiMash batteries powered tons of laptops and cell phones back in the 90s, their biggest legacy, their most important impact, wasn't actually in our pockets. It was on our roads. This new tech was about to become the essential bridge to the modern car era. And why was that? Well, it's because NiMH offered a massive jump in performance. We're talking 2 to 3 times the energy of an old NiCad battery of the exact same size. That huge boost in what we call energy density suddenly made a much bigger application feel possible, actually powering a car. And that is exactly what happened. In 1997, when Toyota launched the Prius, it was that durable, high-capacity NiMH battery pack that made the whole thing work. The success of the Prius was a total landmark moment. It proved to the entire world, once and for all, that battery technology was finally good enough and reliable enough to power a passenger vehicle. But this is where the story of our hero battery takes a really sharp, controversial turn. Just as NiMH was proving its incredible potential, the technology got tangled up in a messy web of corporate patents that many people argue stalled the electric vehicle revolution for a whole decade. Okay, so the timeline is a little complicated, but the gist is this. It starts with General Motors. They bought the key patents for large format NiMH batteries to use in their groundbreaking EV1 electric car. But then, through a series of mergers and acquisitions, those critical patents ended up in the hands of, wait for it, the oil company Chevron. Chevron then created a subsidiary called Cobasys to control the patents, and that's when things got really messy. So here is the absolute heart of the controversy. The allegation is that this new patent holder, Cobasys, made a very specific rule. They would happily license out the NiMH technology for the small battery packs you needed for a hybrid car like the Prius, but, and this is the crucial part, they allegedly refused to license or sell the big, large format batteries you would need for a fully electric vehicle. And this wasn't just a rumor. When Toyota tried to move ahead with a fully electric version of its RAV4 using these big NiMH batteries, they got hit with a patent infringement lawsuit. And that lawsuit forced them to shut down production. So you can see the question that still hangs over this whole story. Was this a deliberate move to protect oil interests by keeping the all-electric car off the road? Now, whatever the intent was, the impact of this patent fight was undeniable. It sent the entire auto industry on this massive detour, and it fundamentally changed the path of EV development for years to come. With the large NiMH batteries essentially locked away by these patents, car makers had no choice. They had to give up on the technology for their all-electric dreams. The whole industry was basically forced to pivot and just wait around for a totally different chemistry, lithium-ion, to get powerful enough and cheap enough to work. And that's why many experts now look back on this whole period as a potential lost decade for the electric car. Yeah, I know. It sounds like a weird question, right? A 70s oil crisis and your smartphone? What's the connection? Well, believe it or not, that crisis is exactly where our story kicks off. The whole journey to the battery that powers your life didn't start in some Silicon Valley tech lab. It started in the panicked boardrooms of big oil. And get this, the 3 scientists who ended up sharing the Nobel for this thing, they never even worked in the same room. Not once. But together, they kind of passed this baton of discovery from one to the next, each one solving a piece of a puzzle that, well, it kept literally blowing up in the other guy's face. Seriously. All right, so let's start with that first unlikely spark. It was born from a crisis that had absolutely nothing to do with electronics and everything to do with the gas you used to put in your car. So picture this. It's 1973. The OPEC embargo hits, and bam, oil prices quadruple overnight. Exxon, one of the biggest oil companies in the world, starts to panic. They're thinking, is this the end of the oil age? So they do something pretty radical. They throw a basically unlimited budget at some of the world's brightest scientists and give them this huge, simple mission: solve the energy problem. Go figure it out. Okay, so one of those scientists was this brilliant British chemist, M. Stanley Whittingham, and he was obsessed with this idea called intercalation. Now stay with me here. It sounds complicated, but it's not. Imagine you're sliding a playing card into a deck and then pulling it back out. That's kind of what intercalation is, but with lithium ions and a crystal structure. Being able to do that over and over again, that's the holy grail. That's how you make a rechargeable battery. And with this key insight, Whittingham makes this huge breakthrough. But, as you can probably guess from the title here, it came with a really, really dangerous flaw. So he actually builds a battery. On one side, the positive terminal, the cathode, he uses titanium disulfide. And on the other side, the negative terminal, or anode, is made of pure metallic lithium. And the result? It was incredible. A battery that produced 2.5 volts for the time, that was huge. Exxon was over the moon. They're seeing this future filled with electric cars, all powered by their technology.
But here's where things get dicey. As the battery was charging and discharging, that pure metallic lithium just didn't want to behave. It started growing these tiny, sharp, needle-like whiskers called dendrites. And these dendrites would just keep growing right across the battery until, zap, they touch the other side, causing a short circuit. And when you short circuit something as flammable as lithium, yeah, you get fire. Lots of it.
And we're not talking about a one-time thing. This happened a lot. Whittingham himself even joked later that the local fire department basically had a reserved parking spot at the lab. You can imagine the Exxon execs weren't exactly thrilled about having fire trucks show up at the front gate all the time. And then, to top it all off, in the early 80s, oil prices completely collapsed. The panic was over, the urgency was gone. So faced with this battery that was, just way too dangerous, Exxon slashed the budget and sold off the whole project. And just like that, the first leg of our relay race was over. The lithium dream, it looked like it was dead in the water.
But the story doesn't end there. That baton wasn't dropped for long. It was about to be picked up all the way across the Atlantic by a physicist who decided to attack the problem from a completely different angle. And what he did, well, it sparked a true revolution.
Okay, so enter our next player, John Goodenough. An amazing name, right? So Goodenough looks at all the fire and explosions coming from that lithium anode, and he basically decides, you know what? Not my problem. He figured someone else would eventually solve the anode issue. So instead, he focused all his attention on the other side, the cathode. He had this theory that using metal oxides could let him store and release those lithium ions at a way, way higher voltage.
And guess what? He was totally right. By 1980, Goodenough's team had developed a cathode made of lithium cobalt oxide. And the result? A battery that produced a staggering 4 volts. This wasn't just a small step up. This was a quantum leap, a total game changer for energy density. I mean, just look at this jump in power. It was immense. Goodenough's new cathode nearly doubled the voltage of Whittingham's original battery, and it was about 3 times more powerful than the standard nickel-cadmium batteries that were in everything back then. All of a sudden, you could use just one of his new battery cells to do the work of 3 of the old ones. That's incredible. But here's the catch. It was an incomplete revolution. He basically created this super powerful engine, but he still didn't have a safe car to put it in. If you paired his amazing new cathode with that old metallic lithium anode, you'd just get a much more powerful explosion. The puzzle still wasn't solved.
Okay, so this brings us to the final leg of our relay race. We're going to see how the last crucial piece of this puzzle was finally put into place. And it didn't happen in the US or in the UK. This time, the action moves to Japan.
So a researcher in Japan named Akira Yoshino, he knew all about Goodenough's powerful 4-volt cathode, and he zeroed in on the real problem, that metallic lithium anode had to go, period. So he started methodically testing all sorts of carbon-based materials, and then he found it, petroleum coke, which is just a byproduct of refining oil. It had this perfect layered structure that could safely hold on to those lithium ions without forming those dangerous dendrites. He had found the missing piece. And this led to the final, really elegant concept. Yoshino took his new carbon anode and paired it with Goodenough's powerful cobalt cathode. What you get is a battery with absolutely zero metallic lithium inside. Instead, you just have lithium ions that shuttle, or, rock back and forth between the two sides. And the simple equation is this. No metallic lithium means no dendrites. And no dendrites means no more fires, no more explosions. And to prove just how safe it was, Yoshino did this awesome, really dramatic test.
He took his new battery prototype and just dropped a heavy iron block right on it. Now remember, any of the earlier versions would have basically become a bomb, but Yoshino's battery, it just got a little warm to the touch. That was it. The safety problem was officially solved.
So at this point, the science is finally complete. But, a discovery in a lab is one thing. Getting that technology into the hands of millions of people, that's a whole different challenge. And that's where a huge consumer electronics giant comes into the picture. Think back to the late 80s. Sony was on top of the world, but their biggest product, the Handycam camcorder, had a major flaw: the batteries. Those old nickel-cadmium packs were heavy, they died super fast, and customers were getting really frustrated. Sony desperately needed a better battery. And wouldn't you know it, Yoshino's safe, powerful, and super lightweight battery was the perfect answer. And from here, things moved fast. After all those decades of slow, careful research, Sony grabbed the technology and ran with it. They had to overcome some huge manufacturing hurdles, but by 1991, they released the world's first commercial lithium-ion battery. The tech was finally out of the lab and in our hands. And the impact was, it was immediate and it was profound. All of a sudden, gadgets could be way smaller and lighter. Their batteries lasted so much longer, and best of all, they got rid of that super annoying memory effect. Where you had to completely drain your battery before you could charge it again? That was gone. That new flexibility is what paved the way for everything: slim laptops, cell phones, and eventually, the entire smartphone world we live in today. When you think about it, every giant leap forward for humanity has been about how we find and use energy, right? From mastering fire, to the steam engine, all the way to splitting the atom. Well, we're gonna look at one of the most transformative, yet kind of overlooked leaps in that entire history. It all kicked off with the quiet little click of a camcorder powering on. And this wasn't just another gadget hitting the market. No, this was the first domino to fall in a technological cascade that has basically cut the cord, freeing us from being tethered to a power outlet. Okay, to really get why this was such a big deal, we gotta rewind the clock a bit. Let's go back to the world before 1991. The whole idea of portable electronics in the late 80s was, it was hitting a wall, totally held back by these heavy, clunky, and just plain inefficient power sources. Back then, the workhorse was the nickel-cadmium battery, or NiCad. And honestly, it was plagued with problems. First, it had a super low voltage, just 1.2 volts. And then there was the infamous memory effect. If you didn't drain it completely before charging, it would basically remember that smaller capacity, and poof, your battery life was permanently shorter. Now, scientists knew lithium was the holy grail. It's the lightest metal, and it has the highest electrochemical potential. The problem? Early attempts to use pure lithium, they were a disaster. They would literally explode. During charging, these tiny, needle-like things called dendrites would grow, pierce the internal barrier, and cause a massive explosive short circuit. Not good. So how did they solve this seemingly impossible problem? Well, a team at Sony, led by a guy named Yoshio Nishi, did something brilliant. They didn't try to tame the beast, that volatile metallic lithium. Instead, they just sidestepped the problem entirely. They found a new way to contain it. And the secret sauce was this concept called intercalation. It's a fancy word, but the idea is pretty simple. They ditched the pure metal and used a carbon material instead. This carbon could safely house the lithium ions, kinda tucking them away between its molecular layers. The ions could be stored safely without any of those dangerous explosive reactions. And this is where the elegant rocking chair mechanism comes in. When you're using your device, the lithium ions rock from one side, the carbon anode, to the other side, the cathode, and that movement creates electricity. When you plug it in to charge, they simply rock back. That's it. No dangerous chemical changes, just a safe, stable, back and forth process. The safety problem was completely solved. And the result was this number right here, 3.6 volts. Now, that might not sound like a lot, but believe me, it was revolutionary. At 3 times the voltage of the old nickel-cadmium cells, a single one of these new batteries could do the work of 3 of the old ones. For product designers, this was a game changer. It meant battery packs could suddenly be way, way smaller and lighter. So what happens when you unleash this kind of power? Well, this breakthrough immediately started to change everything in the world of electronics. It wasn't just a little step up, it absolutely blew the doors off what everyone thought was possible. And the ball started rolling fast. It all began with that Sony camcorder.
But it was the laptop that really made this battery a star, especially Apple's PowerBook, which pretty much defined the modern notebook as we know it. Soon, the 1860-50 cell became the industry standard, which meant massive production, falling costs, and by the late 90s, energy density had nearly doubled again.
Suddenly, designers weren't shackled by the battery anymore. They had a power source that could actually keep up with their ambitions. Screens could get brighter, processors could get faster, hard drives could get bigger, all without killing the battery life. This freedom allowed engineers to totally rethink what a portable device could even be, and that led directly to the sleek, powerful gadgets we all use today.
But this incredible pace of innovation, it wasn't all smooth sailing. As manufacturers kept pushing to pack more and more energy into smaller and smaller spaces, the margin for error shrank to basically zero. And that brings us to 2006, when the industry got a huge wake-up call. Sony had to recall millions of laptop batteries. It turned out that tiny, microscopic little bits of metal were getting into the cells during manufacturing. These tiny contaminants could cause an internal short circuit, leading to overheating and, fires. It was a really stark warning. Storing this much energy demands almost perfect manufacturing. But that crisis, as bad as it was, forced the industry to grow up fast. They learned their lesson and manufacturing scaled up to these massive new gigafactories. And as a result, something incredible happened to the price. Just look at this. The cost to store a kilowatt hour of energy has absolutely plummeted. We're talking a drop of over 90% since just 2010 alone. And because of that crazy cost drop, the battery isn't just a component in your phone anymore. Not even close. It's become the absolute centerpiece, the fulcrum, of the entire 21st century economy. It's the key to electric vehicles, to storing power for the entire grid, and it's at the heart of a global industry with some intense geopolitical competition.
Long-range electric cars feel like they just showed up on the scene, right? But the dream of driving one is actually over a century old. For decades, it always hit the same exact wall, the battery. So how did we finally crack the code? Well, the answer is a lot stranger and honestly way more interesting than you'd think.
Okay, so let's get into it. To really understand the breakthrough, you first have to understand the failure that came right before it, a story that almost buried the electric car for good. So let's rewind to the late 1990s. We're talking about a car that was supposed to be the future, the General Motors EV1. I mean, it was sleek, it looked like it was from a sci-fi movie, and it was this massive effort from one of the biggest car companies on the planet.
But here's the thing, its life was incredibly short. It launched in '96, got a little battery upgrade in '98, and then, poof, the whole program was canceled by 1999. And the big reason why it failed? Well, it all came down to that one critical part, the battery.
The first generation was running on old-school lead-acid batteries, which gave it a range of maybe 60 to 80 miles. I mean, that's barely usable. The upgrade to nickel metal hydride, or NiMH, was a bit better, sure. It pushed the range up to 140 miles on a really good day. But that technology was a total dead end. The batteries were ridiculously heavy, super expensive, and if it got too hot or too cold, forget about it. The performance just fell off a cliff.
So after GM famously went and crushed most of the EV1s, they literally crushed them, the entire auto industry basically threw up its hands. The consensus was that batteries were a bridge to nowhere. The real future, they all decided, was hydrogen fuel cells. So the electric car, it was dead, done, over.
But then, around 2008, this little startup out of Silicon Valley shows up with an idea that was, it was completely heretical. And here's the key part. They weren't a car company. They were looking at this whole problem from a totally different world, the world of consumer electronics.
So what was their secret weapon? It wasn't some huge, custom-designed automotive battery. No, they picked this, the humble 18650 lithium-ion cell. This little guy was the standard battery you'd find in basically every single laptop back then. And to the big, traditional car engineers, this was just insane. These small cells weren't built for the stress of a car, and they had a bit of a reputation for, catching on fire.
And that right there, that was Tesla's huge gamble. Their wild idea was to just forget about making one big battery. Instead, they said, let's just take thousands of these little laptop batteries, we're talking nearly 7,000 of them, and wire them all together into one giant battery pack. To everyone else in the auto industry, this sounded like a complete nightmare, a safety and manufacturing disaster just waiting to happen.
So the big question is, how on earth did they pull it off? Well, it came down to two brilliant innovations. First, they built a super smart computer, a battery management system, that acted like a tiny guardian, watching the health of every single one of those thousands of cells 24/7. And second, and this part is absolutely crucial, they built a liquid cooling system. Think of it like a radiator for the battery, with these little tubes snaking all through the pack to keep every single cell at its perfect temperature.
And the result? It was absolutely staggering. I mean, look at this. The best the EV1 could ever do was 140 miles. The very first Tesla Roadster, powered by all those laptop batteries, got over 240 miles of range. This wasn't just a little improvement, it was a total game changer. It completely rewrote the rules of what an electric car could be.
This success created this huge fork in the road for the whole industry. Tesla had proven that its high-tech, kinda complicated approach worked for a premium car. But a couple years later, in 2010, another major automaker, Nissan, jumped into the ring with a totally different philosophy for the first true mass-market EV.
And man, the two approaches couldn't have been more different. For its high-end Model S, Tesla doubled down on their strategy. Thousands of small cells, all kept perfectly cool with active liquid cooling. Nissan, though, was building the Leaf for everybody, so they chose a simpler, much cheaper path. They used just a few large, flat pouch cells, and they decided to cool them passively, with just the air flowing around them. No liquid, no radiator, just airflow. And that one decision, to skip the liquid cooling, to save money and complexity, was about to teach the entire industry a really, really harsh and very expensive lesson about the fundamental chemistry of batteries. So what happened? Well, without active cooling, the Leaf's battery was just totally exposed to the elements. So if you lived somewhere hot like Arizona, the batteries would literally just bake in the summer heat. The result was a disaster for owners. They watched their car's range just plummet, with the batteries losing huge amounts of capacity in just a couple of years. And that was the big aha moment for every car company in the world. The lesson from those early Leafs was undeniable. Managing a battery's temperature isn't just a nice feature. It is an absolute requirement if you want the battery to last. That seemingly complex and expensive liquid cooling system from Tesla, turns out that was the key. And it's exactly why virtually every EV made today has one. Just take a second to look at that number, 93%. Between 2010 and 2025, the price of a lithium-ion battery pack is on track to fall by 93%. We're talking about going from over $1,400 per kilowatt hour all the way down to about $100. That is the kind of price crash that literally changes everything. It's the reason EVs are finally becoming a real thing for everyone. So the big question is, how on earth was that possible? You know, the easy answer, the one you hear a lot, is just innovation. You imagine some magical breakthrough in a lab somewhere. But that's not the real story. It's not even close. The truth is actually a lot more predictable, way more strategic, and honestly, a lot more fascinating. To really understand this revolution, we have to push past that vague idea of random genius moments. We need to look at the underlying formula. A predictable rule of manufacturing that was basically just waiting for someone to apply it on a massive scale. And this right here really gets to the core of it. The common view is that this was all about a series of unpredictable eureka moments with new battery chemistries. But the reality? This incredible price drop was the totally predictable result of a known manufacturing law. This wasn't magic, it was math, and it was applied with just brute industrial force. And here is that formula. It's called Wright's Law. It's a really simple but incredibly powerful idea. The more you build of something, the cheaper it gets to build the next one. For batteries, it worked like clockwork. Every time the total number of batteries ever produced in the world doubled, the cost to make them fell by about 18 to 20%. So the key wasn't some new discovery, it was just production volume. It was all about scale. Okay, so if scale is the answer, what was the engine? How did the industry actually achieve that doubling of production again and again and again? Well, the answer came in the form of a totally new kind of factory, one built on a scale nobody had ever seen before. This quote really nails the core idea. The Gigafactory, which Tesla made famous, wasn't just about being big for the sake of being big. It was designed from the ground up for one purpose: to put Wright's Law into overdrive. It wasn't just a factory, it was a perfectly integrated system designed to squeeze every single penny of inefficiency out of the process. And the logic is almost deceptively simple. Instead of having this massively complex global supply chain, shipping different parts and components across oceans, you do everything under one gigantic roof.
You've got raw chemicals coming in one door and fully finished, ready-to-install battery packs rolling out the other. This integration just obliterates huge logistical costs and lets you optimize the process relentlessly.
And that obsession with optimization didn't stop at the factory walls. Nope, it went all the way down to the fundamental building block of the entire battery pack, the individual cell.
You see, the industry made a crucial shift from the older, smaller 1865 cell to the newer, bigger 2170 format. Now, that might not sound like a huge deal, but the impact was enormous. The bigger cell can hold more of the energy-producing stuff relative to its metal casing, which means higher energy density. And critically, because each cell has more juice, you need fewer of them, and fewer expensive, time-consuming welds to build a battery pack. It's a cascade of savings that makes everything simpler, faster, and of course, cheaper.
So we have Wright's Law, and we have the Gigafactory. That's the technical playbook. But there's another piece of this puzzle that's just as important, if not more so. And it has nothing to do with engineering. It's all about industrial strategy. For that, we have to look at the incredibly decisive actions taken by China. You know, while a lot of the world was mesmerized by the Silicon Valley glamour of Tesla, China was playing a completely different long-term game. They realized they couldn't beat the old guard at the game of gasoline engines, so they decided to bet their entire industrial future on the next big thing: electric vehicles, and more importantly, the batteries that power them. A masterstroke in this strategy was something called the whitelist policy. From 2015 to 2019, if you wanted to get one of the Chinese government's generous EV subsidies, your car had to use a battery from an approved domestic supplier. This move effectively locked out the established foreign giants, companies like Panasonic, LG, and Samsung, from the biggest and fastest-growing EV market on the planet, right during its most critical growth spurt. This policy created what was essentially a protected walled garden. Inside this garden, domestic companies like CATL and BYD were shielded from their biggest international competitors. They used that protected time to perfect their tech, build out their own gigafactories, and lock down global supply chains for critical minerals like lithium and cobalt. They were scaling up at an absolutely epic level.
So what happens when those walls finally come down? When the policy ends and the market reopens to the world? Well, the result of this potent combination, Wright's Law plus a determined national strategy, had fundamentally redrawn the map of an entire global industry.
By 2019, it was a completely different world. The Japanese and South Korean companies that had been dominant just a few years earlier were now facing down new Chinese giants who had built up unstoppable momentum. The entire center of gravity for the battery industry had shifted, and it had shifted decisively to China.
And the result is what you see right here. The numbers are just staggering. China's CATL, a company many people had never even heard of a decade ago, now controls over a third of the entire global market. And if you add in BYD, Chinese firms hold about half of the whole pie. This was no accident. This was the direct outcome of applying a manufacturing law at immense scale, turbocharged by a deliberate and ruthless industrial strategy.
For a long time, it really seemed like the entire industry was marching in the same direction, toward one single battery solution. But then, everything changed. And that shift led us to what you could call the Great Battery Divergence. Right around 2020, that dream of having one perfect universal battery chemistry for every single EV it shattered. The market completely split, creating two totally distinct paths, two families of batteries, and each one was chasing a very, very different price. So on one side, you've got NMC, that's nickel, manganese, cobalt. It's all about one thing, pushing for the absolute maximum range, squeezing every last possible mile out of a single charge. And on the other side, you've got LFP, lithium iron phosphate. Its goals are totally different, rock-solid safety and, crucially, affordability. So you see the conflict, right? Range versus cost, power versus safety. This is the fight. Okay, so let's start with the reigning champion of the premium car market. This is NMC, the undisputed powerhouse of the battery world. So what you're looking at here is a timeline of a relentless obsession with one single element, nickel. See, nickel is the special sauce. It's the active ingredient that actually stores the energy. So the strategy was pretty simple. You want more range? You got to pack in more nickel. And that's exactly what they did. The industry went from early versions with equal parts of everything, all the way to the latest cells that are over 90% nickel.
And the result of cramming in all that nickel is an absolutely incredible specific energy. We're talking over 270 watt-hours per kilogram. Now, this is the secret that enables those insane, headline-grabbing 400 or even 500-mile ranges you see in the luxury EVs. But, and this is a big but, all that performance comes at a really steep price.
And here's that trade-off. It turns out the more nickel you add, the less stable the battery becomes. These things are much more prone to something called thermal runaway, which is basically a chain reaction that can lead to incredibly intense fires that are almost impossible to put out. They also rely on expensive and pretty volatile materials like cobalt, which has a whole host of ethical and supply chain problems. And all that risk means you have to build these heavy, complex, and super expensive safety systems around them just to keep everything in check.
All right, so while NMC was out there chasing raw, unadulterated power, a completely different philosophy was starting to take hold. An overlooked underdog was quietly staging a remarkable comeback. Let's meet LFP, the safe and savvy choice.
You know, for years, automakers outside of China just basically ignored LFP. They looked at its lower energy density and just wrote it off. They thought, that's a low-end chemistry. It's good enough for a power drill, maybe a city bus, but no way is it going in a high-performance car. Well, they were about to be proven very, very wrong.
LFP's fundamental chemistry is its superpower. The chemical bond in lithium iron phosphate is incredibly strong, and that makes the battery intrinsically safe. We're talking almost immune to those thermal runaway fires we just talked about. On top of that, it can be charged thousands and thousands of times with barely any degradation, and get this, it doesn't use any of that expensive, controversial cobalt. And the result of all that? A complete market revolution. By 2024, the chemistry that was once dismissed as low-end had captured nearly half of the entire global EV battery market. So how on earth did this happen? How did a weaker chemistry become so dominant? Well, it turns out it wasn't just about chemistry. It was about brilliant engineering.
And that brings us to the key innovation that really changed everything for LFP. This is the blade battery breakthrough. This whole thing raises a really critical question, right? If the individual LFP cells store less energy than NMC cells, how can the final battery pack possibly compete with those high-performance cars? Well, the answer wasn't found in a chemistry lab, it was found in the engineering department.
Okay, so check this out. The traditional way of building a battery pack was pretty inefficient. You'd take your little cylindrical cells, bundle them into these protective boxes called modules, and then you'd bundle those modules into a final pack. You're wasting a ton of space. But the Chinese manufacturer BYD completely flipped this on its head. Their blade battery uses these long, thin LFP cells that are so strong they actually become part of the pack's structure, which means you can get rid of the modules entirely. And by just getting rid of those bulky, space-wasting modules, they increased the amount of room available for the actual battery material by over 50%. It meant they could suddenly cram way more of those less dense LFP cells into the exact same amount of space, which started to seriously close the performance gap with NMC. And this created this beautiful paradox. A battery made from a chemistry that was technically less energy dense was now achieving a total pack energy density that could compete with the big dogs. So suddenly, you could have a battery that was way safer, dramatically cheaper, lasted longer, and had a comparable range. This is the breakthrough that convinced Tesla to switch to LFP for its standard range cars, and then the rest of the industry had no choice but to follow.
But wait, the story doesn't end there. Of course it doesn't. This constant battle between range and cost has led the entire industry on a new quest to find a Goldilocks solution. You know, something that's not too hot, not too cold, but just right. And so, enter LMFP. The idea here is brilliantly simple. You take that super safe, super affordable LFP chemistry that we love, and you just add or dope a little bit of manganese into the mix. This one simple tweak actually raises the cell's operating voltage, and that gives you a solid 15 to 20% boost in energy density, all without messing with the fundamental safety of that awesome phosphate structure. This final comparison really puts everything into perspective. You can see the trade-offs so clearly. NMC is the powerhouse, the undisputed king of energy density, but you pay for it in safety and cost. LFP is the workhorse, the champion of safety, longevity, and affordability, but you give up a little on that top-end range. And then there's LMFP, the Goldilocks solution. It's aiming to be the best of both worlds, promising that incredible LFP safety and lifespan with an energy density that's starting to get pretty darn close to NMC. It might just be the perfect compromise the industry has been waiting for.
Okay, let's get right into it. For the longest time, global power was all about who controlled the oil. But now, as we're all racing towards a green future, a whole new power struggle is taking shape. And it's not about what fuels our cars anymore, it's about what powers their batteries. This is the new geopolitics of critical minerals.
And this quote just hits the nail on the head, right? This massive global shift to green energy, it takes a ton of stuff to make it happen. Our move away from oil isn't really getting rid of dependency, it's just creating a new one. Power is shifting from the oil-rich countries to nations that are rich in these minerals, and, maybe even more importantly, to the superpowers who know how to process them.
So let's start our journey at the very beginning, at the source of one of the most critical battery ingredients out there, lithium. And for that, we've got to go to a very specific and very fragile part of South America. Welcome to the Lithium Triangle. This place is a high-altitude desert. It's one of the driest places on Earth, and get this, it holds more than half of all the lithium we know exists. You just can't overstate how important this place is to the global economy. But how they get that lithium out of the ground? Well, that's where the story gets complicated.
Now, here's what's so different. It's not the kind of hard rock mining you might see in, say, Australia. Here, they get the lithium by pumping this ancient salty water brine from way deep beneath these salt flats. Then they just let it sit in these gigantic ponds to evaporate. It's cheap, sure, but it comes at a staggering price for the environment. And this number says it all. 1 to 2 centimeters per year. What is that? Well, that's the rate that Chile's famous Salar de Atacama salt flat is literally sinking. The whole process uses so much water in a place that has almost no water to begin with that the ground itself is actually starting to collapse.
And look, it's not just an environmental problem. You've got wetlands just vanishing, which threatens incredible wildlife, like the flamingos that live there. But then you've got political problems too. Chile is tightening its grip on the industry, which is scaring off investors. And Bolivia, it might be sitting on the biggest prize of all, but it just doesn't have the roads or the tech to get it to the rest of the world.
All right, let's shift gears and talk about another critical mineral, cobalt. If the story of lithium is about a clash with the environment, cobalt's story, well, it's a story about a deep, deep ethical problem.
I mean, just look at this chart. Over 70% of all the cobalt in the entire world comes from one country, the Democratic Republic of the Congo. When you have that kind of dependency on a single place, it creates massive, massive risks for the whole global supply chain. And inside the DRC, you have this issue of what's called artisanal mining. Now, it's actually a tiny piece of the market, less than 2% today. But it involves people, often working out of sheer desperation, in these incredibly dangerous, totally unregulated mines. And that practice, even though it's small, casts this long, dark shadow over any company that has cobalt in its products. It's a huge ethical headache. So what did the industry do? Well, it moved fast. Those ethical red flags, plus the fact that cobalt's price was all over the place, it just lit a fire under researchers. The big goal now is to design cobalt out of the battery completely. And that's why you're seeing technologies like LFP and sodium-ion batteries really taking off.
Okay, so we've dug the minerals out of the ground, but that's just step one. The next part, the refining, is maybe the most important stage of all. And this is where one country has built an almost unbelievable choke point on the entire global supply chain.
First, let's look at lithium again. It might be mined in South America or Australia, but something like 60 to 70% of it ends up in China to be processed into the stuff that can actually go in a battery. Just let that sink in for a second. The vast majority of the world's raw lithium flows through a single country.
Next up, cobalt. You guessed it, it's the exact same story. More than 70% is mined in the DRC, but then a huge chunk of that, again 60 to 70%, is shipped off to China for refining. This is not a coincidence. You're starting to see the pattern, right?
And finally, we have graphite. This is the key material for the other side of the battery, the anode. And this is the real stunner. China controls pretty much 100% of the world's battery-grade graphite refining, a total monopoly. This wasn't an accident. This was a brilliant decades-long strategy. They decided to dominate the middle of the supply chain, and in doing so, they gained incredible power over the entire global EV industry.
So, faced with this incredible dependency, how is the West supposed to respond? Well, they're scrambling and they're spending a ton of money to build their own supply chains, but they're taking two very, very different approaches. So on one side, you have the US, which is using the carrot approach, just dangling these massive subsidies with its Inflation Reduction Act. On the other side, you had Europe, They tried to create a single, giant champion company to go head-to-head with the competition. The results? Well, they couldn't be more different.
The IRA in America has just opened the floodgates for investment. It's creating this new battery belt that stretches all the way from Michigan down to Georgia. It offers these huge tax credits. We're talking up to $45 per kilowatt hour for batteries made in the US. It's basically paying companies to come build their factories in America.
And then, you have the story of Northvolt in Europe. This was supposed to be the EU's great hope, its answer to the Asian giants. But it all fell apart. The company just couldn't figure out how to scale up production effectively. It lost a massive $2 billion order from BMW, and in March of 2025, it went bankrupt. It sent shockwaves across the continent, and it was this brutal lesson in just how hard it is to compete with decades of manufacturing know-how.
For decades, one single chemistry, lithium ion, has been king. It has ruled the world. Well, that era is officially over. We're now entering a brand new, much more diverse age of battery technology, and we're about to break down exactly what that looks like.
To really get where we're going, you have to appreciate just how unbelievably fast we've been moving. I mean, think about it. In just over 3 decades, we went from the humble little camcorder battery back in 1991 to the very first mass-market EVs in 2010, and now to these absolutely colossal gigafactories that are reshaping entire economies. What started as a niche little chemistry project has now seriously challenged the century-long reign of the internal combustion engine. So, what's the next chapter? Well, first up is the one technology that has been talked about for years as the holy grail of the industry, the solid-state battery. This is the big one, the ambitious moonshot, the quest for the absolute peak of battery performance. So what is it exactly? Well, the core idea is actually pretty simple, but the implications are just profound. A normal battery, the kind in your phone right now, has a flammable liquid sloshing around inside. A solid-state battery just gets rid of that liquid and replaces it with a stable, solid material, like a super thin sheet of ceramic, glass, or a polymer. Now, that simple swap is revolutionary for a couple of reasons. First, and most obviously, getting rid of a flammable liquid makes the battery way safer. But here's the real magic. A solid electrolyte unlocks the holy grail of anode materials, pure lithium metal, and that is the key to a massive leap in how much energy you can store. The payoff for getting this right is just immense. We're talking about potentially doubling a car's range, completely eliminating the risk of fires, and enabling charging speeds that could get you back on the road in just a few minutes. See? That's why everyone calls it the Holy Grail. Okay, but if it's so amazing, why don't we have them in our cars yet? Well, that brings us to this little dose of reality. Solid state has been the next big thing for a very long time. It always seems like it's just over the horizon. The hype is huge, but let me tell you, the challenges are even bigger. Right now, there are basically 3 really stubborn physics problems standing in the way. First, it's incredibly hard to keep those solid layers in perfect contact as the battery expands and contracts. Second, tiny, sharp little spikes of lithium, called dendrites, can literally grow and crack the solid electrolyte from the inside out. And finally, just figuring out how to manufacture these brittle, hair-thin materials at a massive scale, well, that's a monumental engineering challenge. So, while the geniuses behind solid state are chasing peak performance, another technology is chasing something that might be just as important: peak abundance. So let's meet the pragmatic workhorse of the new battery world: sodium ion. Chemically, sodium is a lot like lithium. But here's the kicker: it's thousands of times more abundant and dramatically cheaper. Critically, this means sodium-ion batteries don't need any lithium, cobalt, nickel, or even the copper foil used in today's batteries. So what's the trade-off? Well, they have a lower energy density, so you're probably not going to find one in a high-performance sports car anytime soon. So where do they fit in? Well, the most profound impact is going to be on our power grid. The market for stationary storage is just exploding, and sodium ion is poised to crash prices to record lows. I mean, a cost as low as $7 per kilowatt hour. That's an absolute game changer for making wind and solar power available 24/7. And this leads us to one of the most important ideas in this entire story. These technologies aren't really competing against each other. They're actually splitting the market. It's a concept called bifurcation. We'll use powerful, energy-dense lithium for things like long-range transport, and we'll use cheap, abundant sodium for the grid and for smaller entry-level city cars. This takes a ton of pressure off those critical mineral supply chains. Okay, so far we've focused on making new kinds of batteries. But what happens when the millions of EV batteries already on the road reach the end of their lives? This brings us to the final and absolutely critical pillar of the modern battery ecosystem: recycling.
And this introduces a really powerful concept, the urban mine. The idea is simple. Our spent batteries, they aren't waste. They're a valuable strategic reserve of processed minerals, all concentrated right here in our cities. Our old products are literally becoming our new source of raw materials.
And listen, this isn't some distant fantasy. Modern recycling is incredibly effective. Advanced processes can now recover up to 95% of the critical minerals, the lithium, the cobalt, the nickel, from a spent battery pack. We can actually create a truly closed, sustainable loop.
But why does this matter so much? I mean, why isn't recycling just a nice environmental thing to do? Because it's rapidly becoming a matter of national security.
Think about it. By creating a strong domestic recycling industry, a country can dramatically reduce its dependence on foreign mines and refineries. It helps stabilize those wild price swings in global commodity markets. And by 2030, this urban mine is projected to become a major source of material supply all on its own, finally fulfilling the promise of a truly sustainable energy system. So let's bring this all together. From the absolute moonshot of solid state, to the pragmatism of sodium ion, to the sustainability of recycling, what we're witnessing is the birth of a sophisticated and truly diversified battery future.
If you take away one single thing from this, let it be this: there is no single winner. The future isn't about one battery to rule them all. It's about using the right chemistry for the right job. Abundant sodium for the grid, proven, affordable lithium ion for the masses, and eventually that ultra-high-performance solid state for the truly extraordinary applications. And this isn't something that will happen. It's happening right now. The monopoly of a single energy source is broken. A new, complex, and incredibly powerful ecosystem has been born. The electrochemical singularity has occurred, and our world will never, ever be the same. Thanks for joining us.